All right. And actually, well, I'm going to download this Mathematica code file. We have this partial derivatives, tangent planes, and tangent lines and tangent plane. So from the handouts page, I'll share a screen with this in a second, so remote students can see it. So it comes up. All right. Oh, no, go away. Let's make that a little bigger, a little wider. Let's share screen. Okay, so yeah, what we're gonna do is we're gonna talk about derivatives finally. So let me just first, oh, sorry, I gotta run some of these commands. It's kind of, I'll talk about what these all mean in a moment, but I have to just run them before. Sorry. Okay, here's a function. It's the function. Let me make this bigger, probably. It's the function x cubed minus 5xy squared plus 3y minus 4. So that's a function of two variables. If you graph it, let's see, the positive x-axis is down here. I'm trying to reorient it so the way we would see it in the room. So anyways, it's a weird surface. It's not something I would, off the top of my head, be able to tell you what it looked like, right? We'd have to look at cross sections. We'd have to maybe try to look at contours. So the contours look kind of strange. Yeah, if you set z equals constant here, you're gonna get some weird equation in x and y, right? But if you set x constant, you get some quadratic in y. Maybe we can actually see that. Kind of maybe that the x equals constant cross sections would be like these things here, which look like they could be parabolas. And then the y equals constant cross sections. If y is constant, you get some cubic in x. And this looks vaguely like it could be a cubic equation because it goes kind of down, up, and then maybe it's going to go down again. I don't know. You try to get your bearings on this. It's not easy. It's not the same thing. It's not as easy as when we look at functions of one variable, obviously, where we have such a, oh wait, I have it oriented the wrong way. Yeah, where we have such a catalog of things to deal with. But I just wanted to talk about the surface and then try to talk about what it would mean to look at like derivatives on this surface, okay? So in fact, I have some stuff up here that says f sub x or dx. D is going to be for derivative. There's going to be something called the x derivative and the y derivative, or the partial derivatives we're going to talk about. But let's actually do this. I'm going to go back to the Blackboard and start writing some stuff down. So yeah, so today, begin differential calculus. So we're going to do this for a few weeks, and we're going to do integral calculus for a few weeks, and we're going to do this vector calculus stuff that's a little bit more weird. But let's just, like I said, look at this example. Z equals f of x comma y. And let's actually use this example. What did I say? It was x cubed minus 5xy squared plus 3y minus 4. X cubed minus 5xy squared. I already forgot what I just said. Plus 3y minus 4. Right? And let's think about, I mean, there's going to be a sense, we sort of talked about even maybe the first day of the semester, that the analog of a tangent line should be the tangent plane. But before we even get to that, and we'll get to that very quickly, let's just think about the derivative is about a rate of change, right? It's about an instantaneous rate of change. Derivative in general is supposed to be an instantaneous rate of change. So when you learn differential calculus, you first learn about average rates of change. right? So first, think about average rates of change. And I actually think there was a problem on a problem set where I asked you to sort of do this. Right, when you were looking at contour maps, and you had to go from one point to another in the contour map. So from one XY point to another XY point, find the change in the X and Y, and then also find the change in Z and look at the ratio. Guys, remember that question on the homework? Maybe. And then, okay, so but let's just think about this. Like, so for Y equals f of x, that average rate of change, these ROC for rate of change, is just delta y over delta x, right? Just change in output over change in input. You know, you change the input by some amount, you see how the output changes, you take the ratio. But for z equals f of x comma y, we have we can change x or y or both. And then find the change in z. Yeah, then find the change in z, right? So it's already a more complicated question, certainly than it was for functions of one variable. But what we're going to do first is just sort of like, what if we just change x and don't change y? What's the change in z? Or what if we just change y and don't change x? What's the change in z? It makes sense as like a good first thing to think about, first idea. So maybe just say to get a handle on this, try fixing y, changing x, then computing the change in z. Right, so we could do that for this. I could ask you like, what's the rate of change from like 2,1 to 3,1 or something like that. Right, so fixed y, change x. And so you could plug both those into whatever function you have and compute delta z over delta x, right? So that would be, I guess what that would equal, I don't actually want to necessarily do that here, but that would be like f of 3,1 minus f of 2,1 over 3 minus 2. That's delta z over delta x. Yeah. Does that make sense? We're just fixing y. Okay. But what I want to do is I just want to go immediately, because we know how to do average rates of change. I want to go immediately to instantaneous rate of change. So what about, so this is kind of, you could call this a rate of change in the x direction, right? This is sort of like rate of change in x direction. What about instantaneous rate of change? Like in the x direction? Well, you can imagine approaching this a couple different ways. We could actually write down a limit definition like you do for the single derivative, the derivative of function of one variable. So limit approach. I'll write this down, but then we're going to do something much easier because we're lazy and we've done single variable calculus before. But the limit, let me just remind you. So if y equals f of x, right? How many people think they can quote the limit definition of the derivative off the top of their head? That's very sad. No, I don't know why. It's an instantaneous delta y over delta x though, right? So it's really, if you remember, it's like you could do the limit as h goes to 0 of f of a plus h. I'll just do x, it's fine. F of x plus h minus f of x all over x plus h minus x, which is h. Does that look familiar? Right, you do. Because this is basically you're letting h shrink. And you're just, so you're getting the delta y over delta x for a smaller and smaller interval from x to x plus h. Okay. For y equals f of x, no, y, for z equals f of x comma y in the x direction, we'll define this thing called the partial x. So instead of f prime, we write f sub x at this point. Actually, maybe that's why I want to use a different letter here. Maybe that's why when I wrote this down for myself earlier, I was using a different letter. So f sub x at the point a comma b. Doesn't really matter. I'm just doing a specific point. So what I'm going to do is I'm just going to change x, not y. So it's going to be very similar. Is there a question back there? I thought I saw a hand go up at some point. No, you guys are okay. Okay. Please interject at any time. So here's how you write this. You say, well, I can just change the x coordinate, leave b fixed. So it's actually quite similar, right? It's actually just very similar to the definition of the derivative. Sorry, Olivia. It's kind of, I don't know why these words are so recessed. It's kind of strange. Yeah. A and B is just a point. Like AB is a point in the XY plane. A comma B is a specific point. It's like you want to calculate the derivative at a point, right? In the XY plane, just like x equals A is a specific point. If you're trying to calculate the derivative at a point. Good, good. Anything, other questions? So you can give a limit definition and do limit. And you can imagine doing something similar for in the y direction, right? If I wanted to do the derivative in the y direction, you would fix x and change y. So you'd have like b plus h instead of a plus h. Yeah. So this, let me just put a button on this. This is called the partial x derivative. Of f, x comma y. Okay, so that's called the partial x. But like I said, we're lazy and we don't want to use the limit definition when we can avoid it. Right? We did all the limit definition stuff in Calc 1 and built up all these rules for differentiating. So instead, let's use our knowledge of single variable calculus. So that's kind of one approach. Second approach is use our single variable calculus knowledge so what I mean is, like, let's look at this example now. And let's look at the point, I think I was using the point 2 comma 1 on the Mathematica. Yeah, let's look at the point 2 comma 1. So example, for f of x comma y equals that example up there, x cubed minus 5xy squared. plus 3y minus 4. Let's find the partial x at the point 2, 1 without using limits. I don't think we need to use limits to do this. I think we're smart. We can piggyback on our knowledge of single variable calculus. Kind of one of the things that we do here. Hope people can see that. If you're on the Zoom and you can't read that, let me know. I can zoom in on the board more. Just put it in the chat. So how would we do that? Well, here's the thing. I said fix y, right? We're fixing y and only changing x. So let's actually just fix y equals 1 in this whole function. Just plug y equals 1 in, right? That's kind of the way to do this, I think. So if we want to like piggyback on our knowledge. So the idea is look at the y equals 1 cross section. Of z equals f of x comma y, right? So f of x comma 1 is x cubed minus 5x plus 3 minus 4. So that's just x cubed minus 5x minus 1. Yeah? Let me zoom in a little bit. Yes. Thank you. So probably, oops. Move in here and zoom. Sorry. Okay, good, thanks. Yeah, but actually, let me share a screen for a second. Go back to this this graph here. So notice here, I actually have x cubed minus 5x minus 1. Because it's kind of what, this is gonna look stupid, but let me just run these commands real fast. So basically, right, I think the orange one is the y equals 1 slice of this graph. You guys can see that? And then actually the x equals 2 slice is the blue line, so I have both of these. And then, let me try graphing this. Okay, so there actually is a tangent line to the graph right there, right? Like you can, there's a line tangent to that orange slice. You guys see that? Okay, and so really all we do, I mean, this isn't super, I don't know, impressive, but what I can say is, what we can do is we can just basically say, look, this is a function of one variable right here. We could almost call this like g of x or something like that, right? This is a function of one variable. So, in fact, if we want to think about it this way, the partial x, f sub x of 2 comma 1 is just really g prime of 2. Does that make sense? Because we're just trying to plug in x equals 2 now. We already plugged in x equals 1 to get this function. We're going to plug in x equals 2 to get that. So g prime of x It's easy, right? That's 3x squared minus 5. You guys can still do those derivatives, right? And then, so g prime of 2 is what? 3 times 4 minus 5 is 7? 7. So that actually is the partial x at that point. And it doesn't look like it slopes 7, but if you notice the z, oh, sorry, let me share again. If you notice the z-axis has a much bigger scale, right? This is from 0 to 10, whereas on the x-axis at 0 to 1. So it's really like over, I guess that is at x equals 2. If you go over 1, it does look like you're up to about, well, I guess this height is somewhere below z equals 0. So that's plausible. You've gone up about 7 units on the z scale if you go over 1 unit on the x scale. Yeah. Okay. So does that make sense? That's what the partial derivative. It's the partial x derivative. And we can do something similar with the partial y. That we could actually graph. Yeah, we can plug in. We could plug in x equals 2, right? So see if you can figure out. Maybe I'll give you guys a minute. See if you can figure out the partial y. It's a very similar idea at 2, 1. What are you going to do? Yeah. Yeah, x equals what? Well, y was equal to 1 here. X is equal to 2. Yeah, we're doing 2 here, right? So yeah, let's do the x equals 2 cross section. Right. Good. So figure out plug in x equals 2 to this original function, or to the original function up there, I guess. And get a function of y. Right. So do that for a minute. Do that. It gives me a chance to drink coffee. And you guys do stuff. But I'll write what you said, which is. Looks like it's steeper, right? And maybe negative. Oh, sorry, let me share. Yeah, you guys figured it out? What'd you get for f of 2, y? They tell me what they got for f of 2, y. Yeah. 3y minus 10y squared plus 4. Is that what everybody else got by plugging x equals 2? Right, I guess you get an 8 minus 4, and you get a minus 10y squared. Good. And so what is, let's call this h of y or something like that. That's a function of y. And so then the partial y at 2, 1 is really just h prime of 1. So what do you get? You don't get that big a number. Did I do something wrong? Negative 17? Why do I have, oh, is there a minus? Wait, did I miscopy that? Was it minus 3? I feel like this is steeper than, doesn't this look steeper negative than this does positive? But I got +7 as the slope there, and I get, what did I do wrong? Am I looking at the wrong cross section? Oh, this is the, wait, is this the x equals constant? Oh no, this is the x equals constant cross section. That's what we wanted, right? What did I do wrong? Did I do anything wrong? Am I just? Oh, thank you. Yes, absolutely. I didn't actually differentiate. So it should be. Or the 4 goes away, right? So yeah, okay, silly me. Thank you. So that's just 3 minus 20y, right? Thank you. I knew something. It's good. That's why you look at pictures, because you can tell something's wrong. Pictures. Sorry, it's kind of a random picture, but where'd it go? Yeah, this definitely is more negatively sloped than this was positively sloped, so wasn't thinking. Okay. Yeah, h prime of 1 is, sorry, what's your name? Bridget. Negative 17, yes. Thank you. So negative 17. So that case, right, so partial, yeah, I guess I should say this is the partial x at 2, 1, and this is the partial y at 2, 1. Right, so that's a way for us to compute partials at a particular point, right? Couple points I want to make here now. One is that, you know, we get these 2 tangent lines. If you look at the picture, you get these 2 tangent lines, right? So there's this green tangent line, there's this red tangent line. But everything's happening at the point 2, 1. So if I sort of put all this together, oh, not that, this, I actually wrote the plane down. So if I put all this together, the red and green lines, I have this thing of like looking at a color and saying a different color, so I have to be very careful. The red and green lines form a plane, right? And that really is the tangent plane. I mean, it's kind of weird because it goes through multiple times, but if you can kind of see that it's just touching the surface at that point. Oh, wait, hold on, maybe it's bigger. There are ways to zoom in. Never remember the right key command. Ooh. I don't know that that's going to make it any more illuminating than it was. Yeah, somehow. We'll look at some other examples where it's more obvious, like the bowl example, where we'll really get a plane that just like barely touches the bowl. This, because this is curvy in weird ways, you can end up with the surface kind of like intersecting the tangent plane in weird ways, you know? So, I undo that? Yes. Okay. So, and I'll talk in a second about what the tangent plane is, but actually we can do that. I mean, we can actually write the tangent plane down immediately because we have the x slope and the y slope. That's really what we computed, right? We really found the x slope of the tangent plane and the y slope of the tangent plane. So maybe I'll write that down. And then I want to talk a little bit more about general partial derivatives. So, yeah. Please, any questions about this so far? Just start talking. I'm turned away from the board, away from you guys. We can also write down the tangent plane, the equation of the tangent plane at 2, 1. Now, right? Because the form, well, we'll talk about this. We've actually seen this other form of planes now that you were just looking at, that you've just been looking at for like homework and stuff, that like, you know, A times X minus X naught plus B times Y minus Y naught plus C times Z minus Z naught. And the ABC, those coefficients give you a normal vector. But before, when we did planes, before we actually did Z minus Z naught equals M. Remember, these are the planes that did not include vertical planes. Right? So this did not allow for vertical planes, but we had this where the X slope, this is sort of what we call the X slope. And this is what we call the Y slope. Yeah. And in our example, X naught is 2, Y naught is 1. We actually need to compute Z naught. We need to plug 2, 1 into the original function to get the height of that point, right? And then M is the partial X derivative and N is the partial Y derivative. That's how you did tangent lines, right? You used the derivative for the slope. Does that make sense? So here, M is the partial X derivative and N is the partial Y derivative. And in this example, here I mean just in the tangent plane situation. And in this example, we have the point 2, 1, f of 2, 1. Kind of goofy, but I'm just saying that's what you get for the Z value, right? Go back to the original function, which is no longer on the board, and plug in 2 and 1 and see what you get. Actually, I guess you should just be able to plug in 1. You should just be able to plug in 1 up in there. Is that where the -3 is? That's what I was trying to do before. I was trying to plug in 1 to the function before Bridget caught me in. So it's f of 2, 1, -3. Go back to the original function. Yeah, actually, if you look at the Mathematica, there's a one thing you can do in Mathematica that's nice is you can define functions. So this function, once I define this, it knows that like f of x, y always means this function. And then I just did f of 2, 1, and it tells me -3. And you can also define partial x. This is like the derivative with respect to x. This is the derivative with respect to y. So it gave us, oh, actually, I'll talk about that in a second, general derivatives. But we got these numbers 7 and -17. I just had like it do the calculation for me, you know. Okay, so, right, if you try this, this is actually -3 if you just actually plug it in. So we have the point 2, so this is our x naught, this is our y naught, this is our z naught. M we said is 7, N is -17, and so the tangent plane is z minus -3, which is plus 3, equals 7 times x minus 2 plus or minus 17 times y minus 1. And so that's the tangent plane. You could rearrange, you could also, you could rearrange this in various ways. You could expand this out and do minus 14 plus 17. Oh. Let's go through the origin. Kind of random, but looks to me like 0, 0, 0 actually fits that equation. Doesn't matter. It's not the point we care about, but does that make sense? Okay, so that's how you get the tangent plane. Maybe not. I don't know. I'm trying to look. Oh yeah, maybe it does go to the origin. All right. I just noticed that this was minus 14, and this is plus 17, which gives you 3, and it also has a plus 3. So if you simplified it, it would happen to cancel. Doesn't matter. It's not really the point. All right. But we're good with that. Okay. Calculus, guys. Feel the excitement. I can feel it. All right. So the other thing I want to say is we can actually do a more general partial x and partial y, because we did it like at a point, right? We'd like looked at the cross section and then computed the derivative and got it at a point, right? So we sort of plugged in x equals 1 first. Y equals 1 first here, and then differentiated and then plugged in x equals 2. But you could actually do it. You could plug in the 2 and the 1 after differentiating. If you just think about what we did is we held y constant and differentiated with respect to x, right? So you can actually do that with the letters instead of numbers if you want. So general partial derivative. For partial x, pretend y is a constant and differentiate. Just treat it like a constant and differentiate the x variable. So let me give the example again. For example, for this, we're getting the function 5xy squared, 5x squared y. You guys tell me, what is it? 5xy squared plus 3y minus 4. Pretend y is a constant. Just pretend it's a constant. Just pretend it's like sitting there like a constant, right? Then what is the partial x? If we treat, so this is a general, right? I have x comma y here. I'm doing like a general partial x. So x cubed becomes, someone say it, 3x squared. And then what does 5xy squared become if you're treating y as a constant? Yeah, so you said 5y squared. Yeah, it's like basically this is a linear function of x, right? It's constant times x. Derivative of constant times x is just that constant, right? So that's minus 5y squared. What happens to 3y if we treat it as a constant? It's gone, right? 0. So that's it. So these both become 0. So that's what the partial x, general partial x derivative is. And similarly, for partial y, you do the same thing. You pretend x is a constant and you differentiate y. So what happens to the x cubed? If x is a constant. differentiate. You're waving bye to it. Bye-bye. Yeah, this goes away now for differentiate with respect to y. It's like a constant. We're just treating this like a constant, right? It's what happened when we actually did this. If you look back when we did the specific case, we plugged in a specific x equals constant. This term ended up going away because it was a constant, right? And so that goes away. What happens to minus 5xy squared? Someone tell me. If I differentiate with respect to y. Yeah, minus 10xy, right? Because this is like a y. The x just sits there. It's a constant. But we differentiate the y squared, becomes 2y. So that's minus 10xy plus 3. Minus 4 goes away. So here we're treating x, or to get from here to here, we're treating x as a treat x as constant. Differentiate with respect to y. Okay. Oh, you guys have the answers on screen anyways, because I had the program do it for me. But yeah, so these are the general partials. And then if you could check, if you want to check what's the partial at 2, 1, that's 3 times 2 squared minus 5 times 1 squared, which is the same computation we did before. I remember we had 12 minus 5, right, to get 7. So that works. And the partial y is minus 10 times 2 times 1 plus 3, and that's what we had before. Minus 20 plus 3 was minus 17. Okay, so that's kind of the way we really do it in practice, is we actually do these general partial derivatives. Just like you generally differentiate a function, you don't plug in the point until after you differentiate. Totally, just I picked a random point. Could have done any other point. Yeah, thanks. 2, 1 is a random point. Yeah. Okay. Now then, I guess maybe one other generality I want to say about partial derivatives is that there's a few different notations. That it's worth mentioning. So recall for y equals f of x, we have at least 2 different notations, right? We have f prime of x, and we have dy over dx. That's the Leibniz notation. That's supposed to somehow represent the fact that it's an instantaneous rate of change. That these are supposed to be super tiny change in x and super tiny change in y. You'll even see things like, you probably haven't seen this, but you'll even see things like just df. That's just supposed to be like a new function. df of x or something like that. That, that doesn't come up. You probably haven't seen that before, but some higher math places, people just use like a capital D for the derivative. So I'll just be like something separate, just because it kind of does the same thing up here on this screen. So for partials, we actually do something similar, except, right? I guess actually what I should have written also maybe is, the other thing you've probably seen is just df over dx, right? So yeah, don't worry about the capital D thing. That's kind of random. I don't think it's in our textbook either. So. But then for z equals f of x comma y, the partial x is, like I said, f sub x. There's also this thing, dz dx, but they're kind of like cursive-y, script-y d's. Those are partial symbols. You'll see this in books, like, you may have seen this out in the real world somewhere, You see derivatives all the time in the real world. I know you don't, but so if you've seen people wearing, I don't know, there's certain t-shirts that have like Maxwell's equations and stuff on them that might have some of this. But so these are sort of like, yeah, these are like curly Ds instead of, and it's supposed to indicate somehow that it's not the only, this is only a partial derivative. It's not the whole derivative. It's not, there are other variables involved. So it's not, you know, if we want to understand the derivative more fully, we'd have to look at the derivatives of other variables. So these are curly Ds. So you'd say like partial Z over partial X. So we could also write df dx. Yeah, we could just say like partial Z over partial X is how we would write that, how we would say that. Okay, yeah. It's a curly D, yeah, it's like, I don't know, it looks like a delta or something. Like if you start looking in the book in chapter 14, you'll see them out, you start seeing, it's not a 2, sorry, this is a D. Yeah, it's not a 2. Oh man, do mine look like 2s? I guess my 2 looks like that. Yeah, that's not a 2, it's a D. Yeah, probably I'm not even writing them. Be careful when you write them. So you could write it that way, right? Partial Y, you can guess, is f sub y, but we could write dz dy or df dy. You can imagine when we have w as a function of x, y, and z, very similar, right? You'd have a partial x, a partial y, and a partial z. And you could have dz dx or dz dy, or sorry, dw dx, dw dy, dw dy. I guess we don't say partial, we just say d, but you draw. It's just to remind yourself, this is not a function just of one variable. Okay. One funny thing that happens, just as a last note, is recall, like we'll talk later about second derivatives and higher derivatives. So like for y equals f of x, we have like f prime of x, and then we have like f double prime of x, right? And so on. Or you can write dy dx, which we think of as, you can think of this dy dx as you're doing something to y, right? It's like ddx of y. And so when we write second derivatives, we can think of this as like d dx of d over dx of y. And that's where you get the like d squared y over dx squared, which really there should almost like be parentheses around the dx here. You know, remember this notation for second derivatives? That's why the 2 is there, because there's like 2, it's like you think about d over dx as like something operating and changing the function. And I could put f here instead of y. So you get that. When you have z equals f of x comma y, you can have like fx. You can have like the second derivative. I could do like differentiate with respect to x twice. I could do I could differentiate with respect to y. Right? I could differentiate with respect to x and then with respect to y. Or I could differentiate with respect to y and then with respect to x. Or I could do fyy. You could do, you know, differentiate twice with respect to y. And then you get some really goofy stuff with like, sorry, I'm just gonna erase this, I shouldn't, but you could write this as like d squared z dx squared. You can write this as d squared z d dx dy. or actually dy dx, I guess, because I did dy second. You could write this as d squared z dx dy, and you could write this as d squared z dy squared. So there's actually 4 second order partials. There's 2 partials, and then there's 4 second order partials. They're called second order, like double derivatives, second derivatives. We'll do this later in the chapter 14, but I just think it's kind of funny, the notations now. Because now this is like I differentiated once with respect to x and then once with respect to y. That's an x and that's a y. Right, whereas, or I can differentiate twice with respect to x, or I can differentiate twice with respect to y. Just saying it's a thing. So, all right, I think we are out of time. Oh, geez, I'm sorry, we're out of time. But anyways, all right, so that's the introduction to derivatives. We already have homework for Friday, but I'll post homework for Tuesday on some of this stuff. And I have office hours now. Yeah. I might add 1 or 2. Yeah, thank you for reminding me. I posted it yesterday, but I might add a problem or 2. And thank you, everyone.